Hi Ji. Today the new chapter we're starting is on interrupts. Can everyone hear me?
Yes, sir.
Yes, sir, we can hear you.
Okay.
Yes, sir.
Okay, so please all mute your microphones. Okay. So this is the outline for today's lecture. We'll be comparing two concepts, polling and interrupt. And then what are the steps when microcontroller is interrupted? Some of the steps are automatically being done in the hardware, and some we have to deal with in the software. And then we have to differentiate between the edge trigger versus label trigger, external interrupt. So there are two in the 8MEGA328P, the microcontroller is that has been used in the Arduino Uno. It has two external interrupt pins, interrupt 0 and interrupt 1. It's labeled INT0 and INT1. And then there is an important concept of interrupt vector table, which we need to understand, and then how to enable or disable the interrupts feature of a microcontroller. And then especially we're using timers this time, using interrupts. Last time we saw that every time we configure a timer, let's say for 100 millisecond or 200 millisecond, we keep on polling or we keep on checking the timer overflow flag and see if it is high or not. And during that time, we don't do anything else. This time, we'll not wait for it. We'll be interrupted every time the timer overflows. Okay, and then we'll see some code in C language. So this is it. Polling, what is polling? And well, you saw an example of polling in the last lecture when the timer flag was not high. We were in a while loop, and that while loop was just waiting for the flag to get high. That method is called polling. And imagine if you're using two timers, then what you'll be doing? Then you have to poll two flags, or maybe all three timers you're using, or you're using ADC and other peripherals of the microcontrollers. Then the polling is not efficient. So this is a basic comparison. What happens in interrupt? It notifies the CPU that a device needs attention. For example, a timer overflows. CPU should know that, oh, it has overflown and we should do something. Um, in polling, CPU has to constantly check, and it occupies the CPUs. And CPU is the most precious resource in any microcontroller. Okay. If we compare the mechanism, so an interrupt is a hardware mechanism. It happens in the hardware. Polling is purely in software. So we are not, even if the hardware is offering us this very extremely useful feature, in polling, we're not getting benefit from that. So that's not an efficient and a good programmer or an embedded system developer would hardly go for polling if there's a very special reason. Otherwise, interrupt is all that we do most of the time. Servicing, how do we service both? In case of the interrupt handler services the device. Okay, so there is a hardware unit in the microcontroller which first serves the device. There is a dedicated unit for that. In case of PC, there is a separate chip for that. But we are talking about the microcontroller. So yeah, so the hardware is handling. Let's say there are 3 interrupts occurring at the same time, 4 interrupts occurring at the same time. Then who will be getting the priority? Who will be served first? Who will be served next? Who will be served last? That interrupt handler takes care of that. Of course, we can configure through software, but ultimately it's the hardware that is doing the job. And CPU services the device in case of polling. So the load is entirely on the CPU. Other comparison, if we compare the two based on the from the CPU perspective, so CPU is disturbed only when a device needs servicing, which saves CPU cycles. And in case of polling, the CPU is in the continuous waiting state. And it means the CPU cycles are being wasted. Occurrence and interrupt can occur at any time. And in case of a polling, CPU polls the device at regular intervals. So even if something might not happen in a minute or in an hour, in a day, still you're just checking it. Just like someone knocks at your door and then you go and open the door. And as an alternative to that, nobody has knocked yet, but you just go and check if there's something at the door, and then you keep on checking. Let's say every 15 minutes or every 1 hour, you just go and check someone at the door, check someone at the door. So that of course is not efficient. In terms of efficiency, interrupt becomes inefficient when devices keep on interrupting the CPU repeatedly. If you know that there will be like 100 interrupts in a second, that means you are expecting 100 pulses from a sensor to arrive in a second. So I wouldn't. That is something that I know for sure that it's happening quite repeatedly. So polling is a good way, good option for that. When does polling become inefficient? When the CPU rarely finds a device. I give you an example of the someone knocking at the door. So if somebody comes and he knocks and you go and open the door, but if you know that there are 100 people coming or 1,000 people coming, and I wouldn't, and everybody, I don't want them to just ring the bell, and I don't want to come over and over and open the door and close the door, open the door and close the door. Then polling is obviously a good option in that situation. If we give real life example, that yeah, I gave you this example already. So these are the, yeah. So now let's look at the software. For example, in on the left you see that the pin 2 of port D, we want to see if there is a 0 coming on that or not. Let's say some device, you expect that that device will be sending you 0, and you really want to know if that 0 has arrived or not. So this is, we are polling it, we're checking it. And in case of interrupt, the same while loop is there like this. But we're not doing if statement here. We're doing nothing. I mean, we can do something else. We can utilize this time for doing something else, like blinking an LED or controlling a motor or sending something to a device, an output device, or listening to some other input device. We can utilize this time. But if you look here, whenever that pin goes low, we are automatically interrupted from here. We leave this loop and we go and execute the interrupt service routine. This is a new term that you are seeing, interrupt service routine, or for short, it's called ISR. It's a piece of code that we write, it's a function that we write, which is executed by the CPU every time an interrupt occurs. So we are not calling it exclusively or explicitly in the software. There's no calling of this function. It's being called automatically by this hardware, and the hardware knows where to go. For example, if there are 5 interrupts occurring, then there will be one interrupt service routine for each one of them, and that will be unique. Okay. So here the name is not very good here because it doesn't mention whether it's an external interrupt or internal interrupt, whether it's a timer interrupt, whether it's an ADC interrupt or serial interrupt. There are a lot of types of that. We'll see that. But generally, from this slide, what you have to take away is in polling, you're doing this check in the software. In interrupt, you're not checking the flag to go low or a pin to go low. You will be notified and you'll jump into that code. You don't have to call the ISR. We never call ISR. Okay. So what is an interrupt controller? So in case of think of this as a separate hardware circuit or hardware unit whose job is to take care of the interrupts. Before sending a certain interrupt to the CPU, we can handle it here first. We can prioritize. For example, we assign, let's say, IRQ0. It's an interrupt request number 0. Let's say it is assigned to timer 0. Interrupt request number 1, let's say that is assigned to timer 1, and so on. And then there are some input output devices which we might have connected to the external interrupt pins, and we have assigned that a unique IRQ. This especially happens in case of a PC. In a microcontroller, there is no such concept as IRQ. But generally, I'm explaining the interrupt concept. All right. So, and then USART. USART is the Universal Synchronous Asynchronous Receiver Transmitter. This is a chip for short that is responsible for the serial communication. So let's say you have a byte of data arriving in the at a certain port, or I'm sorry, arriving at the receiver pin of the microcontroller, and instead of just the CPU waiting for every bit, it wants the entire byte to arrive and then it reads it. Okay, so the USART will interrupt the CPU when the entire byte has arrived in the buffer in a certain register. And same is true for transmitting. In the case of transmitting a byte, we will make the buffer, well, the CPU needs to be interrupted every time the previous byte has been sent completely. Only then it can give it another byte to send. So we'll see a serial communication. We have a separate chapter on that. And then SPI, it's another way of serial communication. It's a serial peripheral interface. And there is another even, these are different technologies for serial communication. You might have heard about I2C. I2C, SPI, USART, these are peripherals. These are ways of doing serial communication. So we can interrupt, an interrupt controller can interrupt a CPU only when a request from any one of these peripherals comes to the interrupt controller. And then the interrupt controller will see if who has the priority. For example, reset is also an interrupt. So every time you pull off the power from your microcontroller, so you're actually resetting it. Or every time you press that reset button on the Arduino Uno board or any board, you're actually resetting the CPU. And the priority of that reset is more than anything else. It's not like, okay, wait, I'm turning this motor, let it rotate by 30 degrees and then I'll restart. No, you have to leave whatever you're doing, you just restart. Because the reset interrupt has occurred and the CPU and the interrupt controller will notify the CPU immediately that an interrupt of a high priority has arrived and you need to reset. You have to leave whatever you're doing. Okay, so these are, so on this slide, I explained different types of interrupts and the role of the interrupt controller. All right, so now let's specifically come to the AVR microcontroller, and especially we're talking about the ATmega 328P. So whatever I'm doing here, they apply to the Arduino, remember that. So it doesn't matter where you program it, whether you program it in the NAIML environment or you program it in the Arduino IDE, concepts are the same. So this highlights the interrupt unit that deals with configuring the interrupts, disabling the interrupts, enabling the interrupts, controlling the interrupts, configuring. That's the most important term, configure an interrupt. For example, I want this interrupt to happen, but I don't want that interrupt to happen. I will entertain the timer interrupt, but let's say I will not entertain the external interrupt. So for programmer, these are the most precious registers that we should know. In case of timer, you saw that the timer control register was the most important, and then there was a timer counter register, TCNT, and then there were a couple of others. And here you see that at least there are 8 registers that you see here: EIMSK, PCICR, PCMSK0, and then so we'll be explaining in each one individually in the coming slides. And then there is a role for the status register also to play here, because remember, status register shows the status of the different operation being going on in the microcontroller. So we'll see how status register is involved in case of of interrupts. There is a single flag in that interrupt flag. Let's go to global interrupt flag, which has a certain role to play. I will explain that next. Yeah, there you go. So, sorry, there were 8 flags in the status register, and there was a carry flag, zero flag, negative flag, overflow flag, I guess, sign flag, and half carry flag, and temporary flag, and now we're interested in the I flag, which is the interrupt flag. So how to use this flag? When does it get high? When does it get low? Who makes it high? Who makes it low? Those are the things to pay attention to in the coming slides. All right, so there's a concept called interrupt vectors. If you look at your left side, it gives you a basic idea of interrupts. So what happens is, for example, you're somewhere in your program, you have written a program, for example, it just takes its input from a switch and blinks an LED. That's the simplest program that you can write. And you're executing it. And that's a normal program execution. And at that time, something happens. For example, you have configured an interrupt, and that interrupt occurs. For example, that was a timer interrupt. Okay. In this case, it's an INT0. INT0 is the external, how to scroll this. All right, it's so hard. Yeah, INT0. Can anyone see INT0 in this? Right. I cannot see at least. So these are the, yeah, this one is external interrupt request 0. This is your INT0. Okay. Uh, and now what happens is every time I'm interrupted, and I know that after interruption, I'll be executing another function. It's called interrupt service routine. And how would I know where to jump in memory to execute that code? Where is that code located? This main program should know. Your loop function should know in case of the Arduino IDE. So it goes to a table first, and it picks up the address of the memory location, the starting address of the memory location, which holds the code that needs to be executed in response to that interrupt. I repeat, you're in a normal execution mode. You were interrupted externally, and that INT0 pin, and from there you note down this address called 0002, and that is actually the from there from well, we jump to the 0002 automatically, and that 0002, from there we will be directed to, for example, a jump instruction will be directed to go here. And that happens in case of all these interrupts that you see on the screen. Reset interrupt, okay, the vector is 000, and then 000 we might write some jump or some other instruction. We'll see examples of C code later on. And similarly, if there is a timer counter 2, compare match A interrupt occurs, the vector is 00E. So I'll jumping onto 000E location here, and from there you can direct me to go to the ISR. Okay, and these are fixed. These are fixed by the people who designed this chip, the admin. Okay, so you don't have to memorize these addresses, but you should know that the vector mean a direction. You will get a direction from here, and hey, you are this type interrupt. Okay, go to interrupt which is located here in the code memory, and then another type of interrupt. Okay, so the hardware takes us to this location. ये ऐसे ही है, मैं उर्दू में एक्सप्लेन करता हूँ कि मुझे किसी बंदे ने चाबी देनी है किसी रूम की, और मुझे वो रूम पता नहीं है डिपार्टमेंट में मैकेट्रॉनिक्स में कि भाई वो क्लासरूम 1 है या क्लासरूम 5 है जहाँ पे कोड पड़ा हुआ है जिसको मैंने एग्जीक्यूट करना है, जहाँ पे मैंने कोई काम करना है. वो बंदा मुझे कहता है कि यार जब आपको ये काम करना हो ना, कोई स्पेसिफिक काम, तो उसकी चाबी मेन ऑफिस में बोर्ड पे इस जगह पे लगी हुई है, और उस चाबी के ऊपर फिर लिखा होगा कि ये किस रूम की चाबी है। आपने फिर उस चाबी को के पास पहले पहुंचना है। तो इसका मतलब है कि जितने लोगों का डिपार्टमेंट में काम है, जैसे ही कोई काम उनको पेश आता है, वो आके इंटरप्ट करेंगे मेन ऑफिस में, बजाय इसके कि मेन ऑफिस के लोगों से पूछे या चेयरमैन से पूछे। नो, वो जाके उसी बोर्ड पे, वो जब उसको पता है कि वो उस रूम की चाबी कहाँ पड़ी हुई है, वो उस बोर्ड के ऊपर जाएगा और वहां से वो चाबी उठाएगा और उसके ऊपर रूम नंबर लिखा होगा या आपने कहाँ जाना है। इसीलिए इसको वेक्टर कहते हैं। वेक्टर मीन डायरेक्शन। ठीक है। Sorry. I think I've explained the concept. More will be explained with examples later on. But this was an extremely important slide. Interrupt vectors. Okay. External interrupts. Let's see some actual interrupts. So the register here that is of importance for us is the EIMSK. I think it means external interrupt mask register. In this case for mask, EI for external interrupt. And you see two interrupts here. The bit number 0 or the digit number 0 is interrupt INT0, and INT1 is the internal external interrupt 1. And those are pin number port D pin 2 and port D pin 3 of the Mega 328. All right. Now look at the slide down and the figure down here. What happens is, let's say you are interrupted on this pin. Which pin? Interrupt 0 pin. Okay. So there is this unit inside the microcontroller which has to detect whether I should be interrupted on an edge, on a rising edge, or on a falling edge, or I should be interrupted on a level. For example, a certain signal goes high and it stays high for 10 milliseconds, okay, or maybe 100 milliseconds, or it stays on forever. So, and in case of a high, we don't want to be interrupted in 10 milliseconds. We don't want to be interrupted 10 times. Or in 10 milliseconds, we don't want to be interrupted once. We have to decide whether we are waiting for the edge to occur and then we'll interrupt the CPU, or a level. So that detector. And how would we configure whether we are using an edge triggered interrupts or level triggered? This bit we have to set, and this is in a separate register called EICRA ISC0. Okay, so they're coming on the next slide. From that, we'll decide whether we are configuring the interrupt as an edge triggered interrupt or a level triggered interrupt. I'll explain that on the next slide. But once, let's say, either edge or level that has occurred for which you were waiting on this pin, now you need to interrupt the CPU. And how would you do that? Sorry. We go to this AND gate and we see whether this flag is 1 or not. That means you have enabled the internal interrupt 0. If this is 0, this AND will never give you 1 here. The output of this AND will be 0 because AND is only 1 if both the inputs are 1. So one input high is coming from an external pin and another is coming from this bit. So if you want to disable the interrupt, just make this 0 through software. Write a program in just one line, make this bit 0. Okay, that means you're masking the interrupt. So externally, something has happened in the door, but you're not listening to it anymore. You just say that, hey, you can ring the bell, but actually, even if I listen to it, I will not respond because I'm busy, or I just don't want to entertain you at this time, unless the software programmer, the embedded system developer, tells me to. Again, how he would tell me, you just go and put 1 in this bit. All right, and then once you're even that is configured and that is 1 and interrupt has occurred, then there is still another AND gate, and that AND gate depends on the I bit of the status register. You saw it here. The I bit, the interrupt, it's called the global interrupt flag. So that means that, hey, the programmer had told me to enable this specific interrupt. That's why I want to see this should be 1. But is the global interrupt flag enabled? I mean, is all the interrupt functionality of the microcontroller has been enabled or not? If that is enabled, then I'm going to interrupt the CPU. That means that nothing has happened by mistake. The programmer knows what he's doing. He has interrupted the global interrupt function, the feature globally, and he has also exclusively enabled the external interrupt 0. Okay, and then I will just put what I'll do is whatever the program line of code the CPU was executing, let's say it was at line number 000E or 005F, whatever. And you know the program counter register, so 16-bit register, it holds the address of the instruction register that needs to be executed next. What it does is the interrupt, it replaces the program counter with a vector. It wants you to go to that main office to the keyboard and pick up the key. So even whatever you were, whoever turn was next, you're not going to the next instruction. Rather, you're going to the 0002 fixed location, in this case, in INT0 case. Now the question comes that let's say we took the key, we went to the room, we did that task, we brought the key, we put it back on the keyboard, but how would I know that where was I interrupted so that I can resume doing the previous work? In other words, I was at room number 5, I was doing something important, and then an interrupt occurred, and then I went to pick up the key, I left whatever I was doing in room number 5, and the other thing was to be done was in room number 10, and I'm done with the thing in the room number 10, and then I put the even key back on the keyboard, then I need to remember where I was. Somebody has to help me that I was in room number 5 before. Okay, so how would we remember that? There is a stake for that. There is a separate piece of memory allocated for that. Whenever you make a jump instruction, remember the current address of the instruction is being stored on the stack. It's pushed onto that. Okay, and that all happens in hardware this time. Okay, so now we are trying to differentiate between the edge trigger and label triggered external interrupts. So if you have put these 4 bits of the EICRA, external interrupt control register A, and then in that we have these 4 bits. 2 for configuring the internal external interrupt 0, sorry, either edge trigger or label trigger, and the other 2 are for configuring the external interrupt 1. Okay, for example, someone told you, or by just looking at your application, you're designing the embedded system, and you decided then, hey, for this particular application, I want to be interrupted on falling edges. So that is your guy. That is your guy. So I want both interrupts to be configured as falling edge. Okay, so 1 0 will go here, and 1 0 will go here, and that's why. Well, oh yeah, they're only making one, configuring only one. So 1 0 will go here. So that's why it's 0 2. Okay. If you want to make external interrupt 1 on falling edge, then you have to put 1 0 here as well. Okay. And for some reason, and by default, they are both level triggered, which means there is a 0 0 0 0 in both. And that's why initially, if you haven't overwritten this with a new value, okay, if you haven't overwritten this with a new value such as this, by default, you're label triggered. Okay. So you have the different application will demand for different ways to be interrupted. Okay, so we'll explore that with time. For now, mostly, sorry, I've seen cases in which we are triggered on falling edge or rising edge. Okay, all right. Yeah, so a question could be that EICRA has been put 08. Now tell me which interrupt has been configured as which type, edge trigger or level trigger. So if you look at the 1000, so it means there is a 1, there is 0, 0, 0. So the answer is interrupt 0 has been configured as a level trigger, and interrupt 1 has been configured as falling edge, edge triggered falling edge. All right. So now let's look at this. Well, I'll skip the the assembly part. Should I? No. Let's go through it because it helps understand the concept very well. So for example, when I start, so this code has been written. So let's understand what this code does. Okay. So right now, this directive tells the assembler to put the jump main function at location number 000. So you can clearly tell me every time the AVR is reset, what will happen? What is it the reset? What the reset location tells us what to do? Anyone? I repeat, I powered on my microcontroller. By default, I'll be executing the location 0000 in the code memory. And what that location tells me to do. What is the instruction there? Hello?
The initializing the first line.
It will read the first line, but what the first line says?
Jump to the main function.
Jump to the main function. Very good. And let's say I'm executing line number 6, which says that load in immediately in register 20 high, let's say some value, and then I'm out sending it into SPH, a state pointer high, that whatever value was, and then I'm executing another instruction, and I'm sending into the state pointer low register, and let's say, yeah. So what this line does, you put 02 in R20 and you put that R20 in the ECRA. So R20 में 02 आ गया. So 02 means this is 0, this is 0, this is 1, 0. So you're actually configuring interrupt 0 as a falling edge trigger. So that's why it's written make interrupt 0 falling edge trigger. And STS because it's a memory location. So we're taking the 02. In C, we would directly assign it by just doing this. But in C, it is done in 2 steps. You already know. You have to put that value in some register, and from that register, you can just put it into memory location. All right. So and then the SBI, it's just setting a certain bit high as an output, DDRB, and then we're activating the pull-up resistor inside this port B pin number 2, and then we're enabling interrupt. This enabling interrupt is actually the EIMSK. We're putting 1 in that. The EIMSK mean we are the status register. No, sorry, not status. EIMSK was here. So if you want to enable this interrupt, you have to put 1 in here. So you're actually putting 1 in here. So that is the next line of code. We'll see in C. The same will happen in the C language. And then we'll give another instruction called SEI. SEI is the set the interrupt flag. Which flag? This one, the global one, which is located in the status register, this one. So SEI is just, and even in Arduino IDE, you might have heard about this function called SEI. It sets the global. So it enables the interrupt functionality of the microcontroller. If you don't do these 2 enables, interrupt 0 cannot be used. And now the question is, let's say I've enabled the interrupts and I'm interrupted. So what will happen? No matter where so I'm doing an infinite loop here. Jump here, jump here, jump here, jump here, jump here. Let's say I'm interrupted. When I'm interrupted, the content of the program counter will be replaced with 0002. That means the CPU will jump to the 0002 location. And from there, I've been vectored to, I've been given a direction to go to external interrupt 0 ISR. You can name it any way you want. My interrupt, your interrupt, external 0 interrupt. And that is here. And I'll go there. And the question is, what is the external ISR? What we are doing in response to the interrupt. So we are actually toggling port B pin number 5 infinitely. No, not infinite, sorry, toggling. So with every interrupt, if we were high, this pin was high, port B, which pin? Pin number 5, we'll make it low the next time an interrupt occurs. And the next time the interrupt occurs, we'll make it high again. The next time the interrupt occurs, we'll make it low again, and so on. So अब इसके जो एप्लीकेशन हो सकती है रियल लाइफ में, तो आप प्रोटियस में भी कर सकते हैं. फर्स्ट असाइनमेंट प्रॉब्लम. इसी प्रोग्राम को असेंबल करके इसका हेक्स कोड जनरेट करेंगे और एक्सटर्नल इंटरप्ट जीरो के साथ आप पुश बटन सेलेक्ट करेंगे, कनेक्ट करेंगे और उससे उसको इंटरप्ट करेंगे माइक्रो कंट्रोलर को, और उधर एक एलईडी कनेक्ट करेंगे. जब जब आप इंटरप्ट प्रेस करेंगे उधर एक एलईडी ब्लिंक करे, तो टॉगल करे. तो मैं ये let me, I think it's already done. No, yeah, no, it's not. So let me put this as a assignment problem. I think this is our assignment for problem 1. Okay, make a circuit for the previous slide where a switch or a push button has been connected to anti-zero pin of the AVR of 8 mega 328p. Every time the switch or button has been pressed, the microcontroller should be interrupted, and as a response it should toggle an LED connected to port B dot 5, pin number 5. Alright, button has been connected to external interrupt this. Every time a button has been pressed, the microcontroller should be interrupted, and as a response it should toggle. Yeah, so make a circuit in Proteus. That will be good. And if you really want to do it, so bonus, make the circuit physically on breadboard or whatever. Okay, so this is problem number 1. So that way you will you'll see what happens. Okay, it's taking time. Okay. Now it illustrates, well, there was some annotations here, I skipped it. So this was important to make the external interrupt 0 falling edge trigger. This was important to enable the interrupt 0, the locally and globally. Locally mean that specific bit for the INT0 interrupt, and global all interrupts of the microcontroller. And this is an ISR for INT0. You might have another ISR for INT1 and so on. Okay, so why don't we do this? All right, it's an interesting thing that comes to my mind. Okay, and that will be modify the assembly language program such that interrupt 1 has been used instead of INT0. So you might change a little bit your circuit and also your code. Okay, and then rewrite the same program in C language. So this will be problem number 1. All right, so let's illustrate what happens when actually an interrupt occurs, and it's a very good illustration. And I told you every time an interrupt occurs, the vector, which is a memory address, has been loaded into the program counter. So by default, when the CPU restarts, the microcontroller restarts, the PC holds the first interrupt vector, and that's for the reset interrupt. So it's 000. That means we start from there. And the interrupt service routine, you can kind of call it for the reset is wherever you write here. You say jump to main. Okay, this main is whenever we'll be interrupted, the reset button is pushed, we'll start executing here from here. And the interesting thing to notice is we are jumping from to main, so we're skipping this vector anyway, this one. Otherwise, we will come on this, and we will just execute it without being interrupted, because we are jumping into the that vector location is automatically come in a sequence. Okay, so the jump purpose was to skip that, and then we interrupt every line of code, and it's just typical execution. Program counter is one more. Then every time we execute an instruction, the program counter holds the address of the next instruction. And let's say we're in the interrupt, and that guy goes low. Oh yeah, wait a second. Why we're interrupted on 0? Yeah, fouling edge. Yeah. So we were high. That means we were high. And it's connected to ground. Yeah. So when it's connected to ground, the transition from the high to low occurred. The falling edge arrived. And now we have to leave where we are. The program counter was holding F000F. That needs to be put into, sorry, I skipped something. Okay, yeah, let's wait for it to go. Okay, the program counter contents. It will be 000 0010, which is decimal. In decimal is 16. So look at that. Interrupt occurred. Now we have to put the next instruction onto the stack because we have to come back here. That's where we were interrupted. And the program counter contents are being replaced with the interrupt vector. And the interrupt vector tells it to go to the interrupt service routine. And we'll come back from that whenever the last instruction has always need to be RETI, return from the interrupt. And now where to return from the interrupt, you already, the stack pointer tells us where to return. Return to the instruction INCR25 where we actually left execution. So this illustrates the use in the use of the stack pointer. This illustrates the use of the sorry, the interrupt 0 external pin. It illustrates the use of the concept behind the interrupt vector because the program counter contents are being replaced by the memory address of the next instruction, the memory address of the instruction, which tells us where the ISR is. वो जो चाबी बोर्ड पे पड़ी हुई है उधर हमें जाना है, वहां से हमें पता चलेगा किस रूम की ये चाबी है. ठीक है? So now let's do timer interrupt. Before I do that, I would like to have some questions. If there is any, please. क्योंकि ये खामोशी जो है ज़रा ज़्यादा खुशाइन नहीं है. लेट्स से कितने लोग बैठे हैं? 29. 29 लोग इतने खामोश तो नहीं बैठ सकते, especially if they are attentive. So when we were reading it the first time, we saw a lot of question in our mind because it's such a new concept. It's so different. It's so interesting and so useful from application point of view. So no question. All right. तो चलिए मैं एक क्वेश्चन कर लेता हूँ randomly किसी बंदे से. अगर so what would I change if interrupt 0 की जगह I would have used interrupt 1? That's my question. In other words, instead of port D pin number 2, I would have used port D pin number 3. What would change in the code here? Which lines of code would you change or would you
Sir,
update?
000B. Sir, enable.
नहीं पहले हाँ शुरू से स्टार्ट लेना, मतलब यहाँ पे कुछ वेक्टर चेंज होगा. मैं दिखा देता हूँ आपको वो स्लाइड जिस पे इंटरप्ट वेक्टर्स गिवन है. तो अभी तक हम 002 यूज कर रहे थे. अब इंटरप्ट 1 के लिए क्या है एड्रेस?
0004.
या So that is the first thing to change. Very good. This will become 0004 because हमें पता है कि जब external interrupt 1 will occur, will be brought to this not this memory location, will be brought to 0004, and from there we can then jump to, well, you don't have to change this because this memory address as long as it's available. अगर ये external interrupt 0 भी है तो फिर इस ISR को नहीं छेड़ना, फिर आपने दूसरा लिखना है. ठीक है, मैं कोशिश कर लेता हूँ. if it doesn't take too long, Control C, and then so let's say I'm told that there are two buttons connected, one to external interrupt 0 and one to external interrupt 1. So I need now two ISR. So I'll just copy this and make it 4, and that should, the meaningful name should be external 1 into ISR. This is the first thing I need to change. And then make internal 0 falling. So decide about the other one. Make, let's say I'm making external interrupt 1 also falling or rising, you can say. Let's say I want to do this rising. So this should be 1. And I need to see what I need to put in the EICRA. So you need to pull out the EICRA register, which was this. I need to make internal 1. External interrupt 1 as rising. So I need to put 1 1 in there. So 1 1 in there means I need to put, I could do this in a single line, by the way, because make interrupt 0 falling and make int 0 rising. Well, that's not a complete sentence. Falling edge trigger and interrupt 0 rising edge trigger, rising edge trigger. So now I need to put 0 2 was because of the interrupt 0. So I need to put 1 1 for interrupt 1. So it's 1 1 1 0. So it should be E. And then you don't need these two. Now how is E? If you look here, you'll understand. 1 1 1 0, which is hex E. So that means I've done that. And then pull up activated because you're connecting a switch outside. It's a good habit. So here you pull up activated for port D pin 2, and I also want to activate it for port D pin 3. So instead of 3, what I should write? Anyone? Oh yeah, this is a set bit. Set bit. Yeah. So I cannot do that on single line. I have to copy this. Control C, and this should be, the third one should also be pull up activated. Pin 3. Yeah. Okay, so that is it. And enable interrupt 0. So I will also enable interrupt 1. Interrupt 1 be enabled kar lunga. And this will be INT1, and that's it. And set interrupt, okay, port B ko be as an output kar dein. It's being configured as an output. And we also need to put the, let's say another LED has been connected to pin number 6. So we're making this 6, and we're doing nothing here. We are making just another external interrupt, and just copy that and paste it, and this will be external 1 ISR. But make sure it blinks the other LED. That was toggling, that was toggling port B5. So this should toggle port B6. And that's it. All right. So now what this program does is, here has to tell me, I wrote this program. I'll copy it here. And, oh yeah, Control Z. कंट्रोल इसको आधा एक में रख लेंगे तो मैनेजेबल हो जाएगा. Let's say all the way to here. Control X, and I just make it like this, or make the layout 2 column. Yeah. So this is 1. Oh yeah, I don't like this guy, and I have to make it extremely small in order to make it fit on a single line. You just have to copy it and compile it. And then this is Control X and Control V, Control A, remove the bullet and just make it small. Okay, so let's call it exercise problem 2 code. Okay, and I can write this as problem 1. Okay, so, and problem 2 is, see the code on the next slide and tell what it does. Demonstrate it's working in Proteus. All right, so this is problem 2 code. Now we are good. This is not, yeah, this is a, okay. This was, yeah. So now timer interrupts. Okay, so timer interrupts, we don't need to do anything. We are doing the same thing as we did previously in the timer chapter. But the thing is, this time the new we'll be doing is how to enable the timer interrupt. What is the interrupt service routine for the timer interrupt? And, well, and how to avoid the polling. Yeah, so when you're using interrupt, you're automatically avoiding polling. Polling means you're not going to check for the overflow flag, whether it has gone high or not. So let's do that. So the important registers for timers interrupts are 3. TMSK0, that's for timer 0, as the name tells. And TMSK means timer interrupt mask register. And there is 1 for each timer. TMSK0 is for timer 0, TMSK1 is for timer 1, and TMSK2 is for timer 2. And now we look at the bits. So which bits are important? For example, if you look at the timer 0, so the first one is will be interrupted if the overflow flag goes high. That has to be 1. And that's not enough. This TOIE flag should be high. That means the timer overflow interrupt enable. Timer overflow interrupt enable. If you haven't enabled the interrupt, even the overflow flag goes high, you will not be interrupted. Similarly, if you have not enabled the global interrupt flag, even these two go high, you still will not be interrupted. So the programmer has to do 3 things. This one you don't make high. This goes high by itself, because whenever the timer overflows, this becomes 1. But this one, the programmer has to enable the timer 0 interrupt and enable the global interrupt. These two we have to do. And then the interrupt service routine for timer 0 is 0020. Okay, so if I can go back to the interrupt vector, so now this is your guy, timer counter 0 overflow. Similarly, there will be timer counter 1 overflow. It's here, 0012. I'm sorry, that's 2. This 001A is for timer 1. 0012 is for timer 2. Okay, so and there are other flags also related to timer interrupts, and you can see them here on this slide. This one. See the output. OCF is the output compare flag. Okay, but you can also be interrupted every time the output compare match occurs. Instead of the overflowing at the 255 in case of timer 0 or FF20, it can be interrupted on any overflow. I mean on the output compare match. And remember there were 2 for each timer. Okay, and that's how we implemented different modes of the timers. In normal mode we go to 255 and then we get rollover. We get overflown, and in the output compare match we just put a value in that register, and that's when we are rolled over. We are overflown. Well, the term for that is not an overflow. It's kind of like a reset. Okay, so similarly there are 2 interrupt flags for that. Let's see some example code on that. And then we have you have to remember where were the overflow flag. It was in the TIFR. You should remember this from the previous chapter. TIFR 0 had this, TIFR 1 had this, TIFR 2 had this. So let's see some piece of code in assembly language again, but the reason we're doing it in assembly language is to see the usefulness of the vector table. And that vector table is actually the location which holds the jump to that certain ISR. Okay, so what should you notice for this assembly code? There are a couple of things you should notice. First of all, initialize your stake pointer. We did not do this before because stake was not being used. This time we know that stake will be put something onto. Stake is a spatial location in memory. You set aside a stake in memory by specifying some address for the SPL and SPH. And we are just putting at the RAM end. We're putting at the very end of the RAM. And RAM end has been defined as or defined in the include files. It probably will be something like 00FFEF or 00FA01. So I'm just randomly guessing. But these 4 lines, sorry, they initialize your stake pointer. Okay, and then like previously, what we are supposed to do is generate a square wave of pin on pin port B.5. And well, we have done some calculation. The square wave has a low part of 2 microseconds and a high part of 2 microseconds. So the full wave time period is 4 microseconds, and the frequency is 1/4 micro, which is 0.25 megahertz or 250 kilohertz. Okay, so that's how it goes. You know these calculations from the previous chapter. I wouldn't repeat again. And load the timer, and then the TCCR0 register has to be put 00 into, because we are making no well, why we are putting this? Wait a second. This means 00 QI, because the mode is a normal mode. Remember, the TCCR0A is a normal mode, and TCCR0 is having 01, which means the normal mode and no scalar, no prescalar, and the hertz of the crystal is 16 megahertz. All right, so and then in this we enable the TIMSK0, and that's how we do it. So that's how you enable this guy, this one. If this is not enabled, the timer function interrupt is not enabled, and that you do here. And then you enable the other flag, the global interrupt flag, and that's how you do SEI, set interrupt, set I flag, sorry. And then you just keep on doing. All right, so what we are doing, we are configuring port B5 as an output. That's why we are putting 5 in there. Remember, as a bit is configured as output if you write 1 into it in the DDRB register. Okay, and then we're outing some pattern on that because we want it to be, we're making that as an input. So this side should be input, and that side should be output. And the thing is the same. Whenever I push this button, this LED should, when I put this button, what should happen? Wait a second, I should see the, um, yeah. So read from port C, we're reading from port C, okay. And in the same time, it's getting data from port C and putting onto port D. So whenever you push this button, this LED should blink, should toggle. And on the port B.5, there is a square wave being generated of certain frequency. So who is doing that? We are taking the input from the pin C and sending it onto port D. We are doing that here. And where we are doing the other thing, because this is an infinite loop, the other thing we are doing through interrupts. So every time the timer overflows, we'll automatically leave this, but it will be for such a short time that nobody will even notice, because we are talking about microsecond. And then humans pushing the button will not be as fast as, at least in microsecond. It will take seconds. And then in that timer 0 overflow flag, what we are doing is we're just toggling port B.5. And every time we do that, we know the timer has overflown, so we are initializing the TCNT 0 again. We're loading the same seed value, -32, because from -32, let's check how is this 2 microsecond. Wow, how is this 2 microsecond? Anyone? Can anyone do voluntarily these calculation? The crystal is 16 megahertz. We're doing no pre-scaling, and we're loading -32 in the TCNT, and they tell us that this is actually the value for generating a 2 microsecond delay. How this 2 microsecond comes from these three calculations, from 16 megahertz, from 32, and from no pre-scaling. Can anyone do it voluntarily? The logic behind the -32? Just guess. Some educated guess. Hello? किधर है आवाम? Is anybody listening even?
Yes, sir.
Yes, sir, we
Alright.
are listening.
So what's the -32 logic behind -32? मैं बता देता हूँ. This -32 is actually, if you can put it in the hex, 32 negative. In hex, it's actually E0. That's a timer 0. So it's E0. So when it will roll, and if you look at the E0, so sorry, E0 in decimal is 224. It's kind of like a positive 224. So what's the gap between 224 and 256? That's 32. 256. Oh, sorry. Go to decimal. 256 multiplied by, well, no, minus 224. That was, I think. This is 32. Yeah. So 32 clock cycles. And each clock cycle is 1/16 megahertz. Okay, so first of all, you just do 1/16. Sorry, we're in decimal. So 1 divided by 16. Wow, it's in the integer mode. I think let's go to the scientific. 1 divided by 16 is this. Yeah. And 1/megahertz is actually, mega will become micro. Yeah. So actually this is 0.0625 microsecond. If we multiply that with 32, we are getting 2 microseconds, and that's how this value comes. I wouldn't repeat it because we are recording anyway, and I want you to burn some fuel on this. But these are the things which you should expect on the exam, these values. And well, there are a lot of concepts in this single slide, but I cannot repeat all because I covered timers last time. But you should be able. So what I can do is, yeah. So let's say this is our problem number 3, slide number 19. Yeah. So perform the animation. Yeah. Not animation. Build, animate the circuit shown on slide, I think that was 19. Yeah, 19. Yeah, where did it go? Slide number 19. In case the slide number changes, it's the timer 0 in interrupt example in Proteus. So this is your problem number 3, and so what it demonstrated, yeah, and put the screenshot in your report assignment. All right, so this was timer 0, and let's see what example is coming. It's the output on the confirmation interrupt. Okay, in change interrupt, we'll do this next time, and priorities we can set, and then we'll see some C code, and the same code has been written here in C code, the one that I just showed you in assembly. So what they're doing is, uh, sorry, I should go through it because you're doing it on an assignment problem number 2. You have to write the C code for the assembly code given. So you know that we're making this port as an output, port B.5, TCNT 0 has been loaded with minus 32. That 32 is actually the gap between the 256 and the 224. You can directly put 224 here. It doesn't matter. And then just normal mode and no prescaler. And then the TIMSK has to be the timer interrupt has to be timer overflow interrupt has to be enabled. And SEI is the set the external set software enable the interrupts. I think that's what it does. SEI. Okay. But it sets the global flag in the status register. Without that, none of the interrupts will work. And DDRC0 make port C input, make port D output, and go into the while loop, keep listening to port number C. Whatever comes in, just through it to the port number D. So we have connected actually a switch outside, and whatever that sends 1 or 0, that will be just shown on the LED connected to port number D, pin number 5. Okay, and then we have written the ISR, and when you include this interrupt.h header file, the interrupt vectors are named uniquely. I repeat, instead of it, what this header file helps you, how this header file helps you is, instead of remembering the memory addresses, the interrupt vectors, it gives you a keyword, which is actually that address, set to that address. For example, this timer 0 overflow vector, it actually, अगर address आप याद रखना चाहें, तो it's actually overflow, timer 0 overflow. it's this 00020. So they have helped us by giving them an English-like name. And I should show you that table also of all these English-like names. कुछ slides में नहीं है तो yeah, here you go. So the timer 0 overflow interrupt, the vector name is this. So the address was there on that slide. The vector name is this, and that's how the Arduino IDE also knows them by this name. So that's why in the ISR you have to specify for which interrupt this ISR is. So these are possibilities. You can put any of these keywords, and then there we just, because we know that timer 0 has overflown, so we need to reset it with the -32 value, the seed value, and then we're just toggling port B. All right, so I stop here. I'll continue from here. If you have any question, that's fine. Otherwise, I'm recording.